on to other theorems now, let's look at angles in a semicircle. Once again, point O is the center of this circle. Let's focus on the diameter, the line segment AB. This diameter divides the circle into two semicircles, but we shall only focus on one of them, the shaded one. From the ends of the diameter, let us subtend angle ACB at the circumference. C can be any point on the circumference within the semicircle. When we measure the angle ACB, we get 90 degrees. That is a right angle. We can move point C around, but the right angle stays unchanged. We can even subtend different angles and observe that they are all right angles. Any angle hanging from the ends of the diameter to any point on the circumference will always be a right angle, leading to the theorem that the angle subtended at the circumference by a semicircle is always a right angle. Yeah, that's right. You can never go wrong on this one, quite literally. Example 4. The question requires you to find the size of the angle marked X and to give a reason for your answer. This is a straightforward case of the angle in a semicircle. The angle is subtended by the diameter, so it is 90 degrees. Since we know two angles in this triangle, X is 31 degrees, such that the sum is 180 degrees for the whole triangle. So X is 31 degrees. Example 5. This question requires you to solve for X and explain the process. Our starting point is this angle whose size is given as 53 degrees. We then consider this isosceles triangle. This angle here is also 53 degrees. Given this is a diameter, this angle must be a right angle. Remember the angle in a semicircle. So, to find X, we need to work within this right-angled triangle and use the fact that the angles must add up to 180 degrees. So X must be equal to 37 degrees. Another theorem. Let's look at angles in the same segment. Let us now focus on the chord AB. As discussed in an earlier lesson, a chord divides the circle into two segments. We shall work within the shaded segment. From the ends of the chord, let us subtend an angle at the point C on the circumference. This angle is in the shaded segment subtended by the chord. Let us now measure the size of the angle ACB. By moving point C along the circumference, we notice that the angle ACB has the same value at all points, so long as 1. We keep it in the same segment, that is, it is always on the same side of the chord. 2. The chord stays the same size. This means that if we subtend other angles within the same segment, all the angles are equal. We can test this by subtending two other angles within the same segment, and we observe that they are all equal. This can extend to any number of angles so long as they are hanging from the same chord and touching the edge of the circle in the same segment. Hence the theorem that angles in the same segment are equal. This theorem holds true for any segment, whether major or minor. Example 6. We need to start by drawing this chord, which helps us get a good perspective of our question. It should then be clear that this angle of 47 degrees is hanging from the chord. We also note that the angle X is hanging from the same chord. Both 47 degrees and X are in the same segment, so they must be equal. X is 47 degrees. Reason: angles in the same segment are equal. Example 7. There is more than one way of solving this example. Let us use the fact that this angle must be 110 degrees because angles in a straight line are supplementary. That means 70 degrees plus 110 degrees must add up to 180 degrees. So to find this angle here, we need to recall that the angle in a semicircle is a right angle. So this is 90 minus 50 degrees, which means the angle is 40 degrees. Now, to find x, we shift our focus on this triangle and find that x must be 30 degrees for the angles in the triangle to add up to 180 degrees. Reason: sum of angles in a triangle is always 180 degrees. Try to think of a different approach and use it to solve for x and still get 30 degrees if you are correct. Now, with x being known, we can find that y is also 30 degrees. Reason: x and y are angles in the same segment. Cyclic quadrilateral. A quadrilateral is a plane figure with 4 straight edges and 4 vertices or corners. Here is a quadrilateral ABCD, and it needs not be regular. A cyclic quadrilateral is a quadrilateral with all its vertices on the circumference of a circle. Each of the 4 edges is a chord of the circle, and the quadrilateral is wholly within the circle. It's an easy act after all, despite the intimidating name. We shall use each of the 4 letters to refer to the corresponding interior angle within the quadrilateral. So we have angles A, B, C, and D as labeled. Let's start by measuring one pair of opposite angles, A and C. As we move the vertices around, we can move either B or D. The values of A and C are changing individually, but their sum is always 180 degrees. B and D is also a pair of opposite angles. By opposite, we mean they are not next to each other. They are across each other with respect to the quadrilateral. If we change one of the angles, the other one also changes, so that their sum is always 180 degrees. So, no matter where the points are located on the circumference, angle A plus angle C is always equal to 180 degrees, and angle B plus angle D is equal to 180 degrees, so long as the 4 points define a cyclic quadrilateral. Hence the theorem that opposite angles in a cyclic quadrilateral always add up to 180 degrees. As an extra exercise, did you notice that moving point A or point C does not change the angles at any of the 2 points? Take a moment and think of a reason why. You could even pause the video and try to figure it out. Okay, let's continue. This is the reason why. If you recall the theorem about angles in the same segment, which we covered earlier, the angle at A and at C are both hanging from the same chord, which is this one BD. But of course they are in opposite segments. Unless we change the length of the chord BD, none of the angles hanging from it will change. Likewise, if you do not change the length of the chord AC, the angles B and D which are hanging from it will remain unchanging no matter where you move the points. Example 8. It is not difficult to identify this diagram as a very straightforward case of a cyclic quadrilateral. Opposite angles in a cyclic quadrilateral always add up to 180 degrees. So, angle X plus 102 degrees should be equal to 180 degrees. So, X must be 78 degrees. Likewise, Y plus 124 degrees equals 180 degrees. So, Y must be 56 degrees. Example 9. The first move to solving this question is to recognize the cyclic quadrilateral and recall that opposite angles add up to 180 degrees. Angles 2x and 3x are opposite each other, so that 2x plus 3x equals 180 degrees. Solving for x gives x equals 36 degrees. Next, we need to consider this arc and the two angles subtended by it, angle y at the center and angle 2x at the circumference. Do you remember the theorem relating such a pair of angles? The angle at the center is twice the angle at the circumference. The angle at the circumference is 72 degrees. That is 2 times 36. So, y should be 2 times 72, giving y is equal to 144 degrees.
Watch the next video. Share with a friend. Subscribe and hit the notification bell icon. Thank you for watching.